Imagine trying to navigate um, a massive pitch black maze.
Okay.
Like you can't see the walls, you can only feel your way forward, and the only feedback you get is this bell that rings if you manage to stumble out of the exit.
Right, which is fine for a small maze. I mean, you bump around and eventually hear the bell.
Exactly. Your brain maps the path. But if that maze is, the size of a continent, you will just wander in the dark forever. You never hear the bell.
You never map a path.
Yeah, you just hit dead end after dead end until you literally stop moving.
And that is exactly the learning landscape we're looking at today. It is incredibly murky, especially when we talk about how artificial intelligence models try to teach themselves really complex reasoning.
Right.
Because the feedback mechanism they rely on that bell, it simply breaks down at the frontier of their capabilities.
Welcome to this deep dive. Today we are unpacking a really fascinating new generative AI paper. It's titled Teaching Models to Teach Themselves: Reasoning at the Edge of Learnability.
That's a great title.
It is. And our mission for this deep dive, for you listening, is to explore this exact hair-pulling problem in AI right now. Like how models hit a total cognitive brick wall when attempting extremely difficult reasoning tasks.
And more importantly, how we get them unstuck.
Yes, because we're going to look at the deeply surprising, almost human-like architecture researchers are using to do that. I mean, honestly, reading this paper totally flipped everything I conceptually assumed about how a curriculum actually builds intelligence.
Oh, it completely upends it. To really understand the brilliant solution these researchers implemented, I mean, we first have to look at the engine driving most of the recent leaps in AI reasoning.
Right, particularly in math and coding.
Yeah, exactly.
Yeah.
So the standard approach right now is reinforcement learning with verifiable rewards.
RLVR.
RLVR, exactly.
So just to break that down, if the system gets the math problem right, it gets a positive reward.
Ding.
Exactly. Right, but you get it wrong, you get nothing. It's a purely verifiable outcome.
And it works incredibly well for tasks where the final state is objectively measurable. The system basically generates hundreds of different reasoning paths.
Just guessing, essentially.
Kind of, yeah.
Yeah.
And when it randomly stumbles onto the correct final answer, the positive reward reinforces the specific logical steps it took to get there.
It creates like a breadcrumb trail of partial successes.
Spot on. So the neural network updates its parameters to favor those successful pathways in the future. The fundamental assumption of RLVR is that the model will occasionally succeed by chance.
Right. You need that lucky guess to provide the gradient to learn.
Exactly. But the breakdown happens when the problem is simply too hard to ever solve by chance.
The breadcrumbs just disappear.
Completely disappear. So the researchers in this paper, they isolated problems from elite math benchmarks. We're talking intense competition-level mathematics.
Stuff that makes my head spin.
Oh, totally. And they ran them through a base model. They specifically chose Llama 3.23b instruct.
So 3 billion parameter model.
Yes. And choosing a 3 billion parameter model as the base is a very deliberate, highly effective experimental design.
Why not use one of the massive frontier models?
Because a frontier model with, hundreds of billions of parameters might just brute force it. Or it might simply memorize solutions from its vast training data.
Ah, which muddies the waters. You wouldn't know if it's actually reasoning.
Exactly. A 3 billion parameter model is, well, it's the perfect crucible. It possesses this vast latent knowledge of mathematical concepts, but it lacks the deep zero-shot multi-step inference capabilities to string them together for, like, Olympiad-level problems.
So it genuinely hits a cognitive brick wall.
Right. It allows us to observe the exact moment the learning plateau happens.
And the plateau they observed was absolute. I mean, on these elite benchmarks, the Llama-based model had a 0 out of 128 success rate.
0%.
Failing 128 times out of 128 attempts.
And a 0% success rate exposes the fatal flaw of these sparse binary reward systems. If the model is completely unable to solve a problem, it receives absolutely 0 positive rewards.
Meaning no gradient signal.
No signal at all.
Yeah.
The model has absolutely no mathematical direction to update its internal weights.
So it's not that the neural network lacks the foundational capacity to, eventually understand the geometry or the calculus.
No, the capacity is there.
But without an initial breadcrumb, it just endlessly wanders that pitch black maze we talked about.
It is left permanently stuck.
Okay, let's unpack this with an analogy for you listening, because this clicked for me when I thought about it this way. It's like trying to learn advanced calculus by only taking a final exam where you just get a pass or fail grade.
Oh, that's a brutal exam.
Right. You don't get your paper back. You don't get red ink showing where you missed a minus sign or applied the wrong derivative rule. If you keep failing, you get absolutely zero feedback on how to improve.
You just stare at the F on your paper forever.
Forever.
Yeah.
You literally can't learn without intermediate steps.
You need a tutor. You need someone to break the calculus down into basic algebra and chain rule exercises before you can even attempt the final exam.
But the bottleneck in the world of autonomous AI training is that having human experts manually curate thousands of perfect intermediate stepping stone questions for every possible complex problem.
It's financially and temporally impossible.
It's just too slow.
Way too slow. And honestly, often the optimal stepping stones for a high-dimensional neural network aren't even intuitive to human experts.
Wow, okay, so the pass-fail test over and over doesn't work, and human tutors are too slow. The AI needs a tutor, but the only tutor available at scale is the AI itself.
Which brings us to the core of the paper. This is where the researchers introduce the SOAR framework.
SOAR, which stands for Self-Optimization via Asymmetric RL.
This is the mechanism built to get the model unstuck. So they started with that pre-trained base model, the Llama 3.23b, and they split it into two identical copies.
Okay.
One is designated as the teacher and the other is the student.
Wait, so two identical neural networks starting with the exact same weights, but they're given completely different objectives.
Exactly. The student's job is to attempt problems and update its parameters based on the outcomes. Just normal learning.
And the teacher?
The teacher's job is to generate synthetic stepping stone problems for the student to train on.
This is so wild.
It really is. It introduces this profound concept to the field, which is decoupled teaching and solving.
Decoupled teaching and solving.
Right. Think about the pre-training data these models absorb. I mean, it's essentially the entire text of the internet.
Which means the knowledge is incredibly vast, but it's super fragmented.
Exactly. The model might not be able to navigate the entire maze of a brutal 20-step calculus proof from scratch, but it possesses the latent, hidden knowledge of all the individual mathematical rules required.
So it has the capacity to generate like a basic three-step chain rule exercise.
Yeah.
Or a simpler algebra question utilizing those underlying theorems, even if it can't solve the grand challenge itself.
Yes. It can build a bridge to a destination it cannot personally reach.
That is just, I marvel at that. So the model already knows how to teach itself. It just needs the right framework to pull those stepping stones to the surface.
That's the idea. It has this latent pedagogical ability to generate a curriculum, because generating a problem is a fundamentally different cognitive task than navigating an unknown solution space.
Right. Writing a test is different from taking a test.
Exactly. So the teacher model can pull those intermediate concepts out of its latent space and present them as stepping stones. But, and this is big, but this latent generation is noisy. The teacher doesn't automatically know which stepping stones will actually help the student escape the plateau.
Because making a teacher model output random math questions is trivial. It could just spit out numbers all day.
Right.
The friction point is knowing whether the synthetic questions it generates are actually useful and not just total mathematical gibberish that just wastes compute.
And this brings us to the critical innovation of SOAR. It's the reward mechanism for the teacher. You have to tether the generation process to reality.
Grounding it.
Exactly. The researchers implemented what they call grounded rewards.
Okay, so the teacher model only gets a positive reward if the student model actually improves on the real ground truth hard problems.
Yes, that original 0 for 128 data set.
So it's a black box grounding signal.
The feedback loop is really elegant. The teacher proposes a batch of synthetic questions. The student trains on those synthetic questions. Then the student is evaluated on the impossibly hard real problems.
The pass-fail exam.
Right. And if the student's score goes up, the teacher receives a reward for that specific batch of synthetic questions, which reinforces its tendency to generate similar structures.
But if the student doesn't improve,
The teacher gets nothing. The teacher is optimized solely on the downstream empirical success of the student.
that makes perfect sense. But we have to contrast this grounded approach with how prior self-play methods attempted this, because the data reveals a massive pitfall in the field.
A huge trap.
Right, because previous frameworks relied heavily on what they call intrinsic rewards.
Right. So instead of testing the student on the ultimate hard problems, the system rewards the teacher based on internal proxy signals.
Meaning intrinsic rewards optimized for localized metrics.
Yeah, exactly. Like, you reward the teacher for generating questions that the student struggles with but eventually solves. Or you reward the teacher based on the perceived complexity of the generated text.
Which, I mean, the logic seems sound. Reward the teacher for creating learnable friction.
It sounds totally reasonable on paper.
But here's where it gets really interesting for anyone listening who loves the data side of this. The SR paper shows that intrinsic rewards are an absolute trap. Relying on those proxy signals leads to catastrophic reward hacking.
It causes a complete diversity collapse in the curriculum.
Let's explain that.
Okay, so when a model optimizes for an intrinsic proxy, it rapidly discovers how to game the system. It finds a highly specific, narrow type of mathematical question that technically satisfies the learnability algorithm.
It finds a loophole.
Exactly. And once it finds that exploit, it completely stops exploring the wider mathematical space. It just generates infinitesimal variations of that exact same question endlessly.
And the researchers quantified this, right? They used something called the Venn score.
Yes, the Venn score.
So for you tuning in, just to clarify, the Venn score is a metric that evaluates the semantic diversity of a data set. It calculates the eigenvalues of a similarity matrix constructed from the generated questions.
Which is a very fancy mathematical way to measure how conceptually varied a batch of text actually is.
Right. So if a model generates 100 questions that use the exact same operations with just slightly different integers, the similarity is high, the eigenvalues drop, and the Venn score just plummets.
And the baseline diversity score for the base model generating naturally was around 34.91.
Okay, 34.91.
And with SOAR's grounded rewards, where the teacher is forced to actually make the student better at the real test, the semantic diversity stayed incredibly rich and broad. It sat around 31.99.
So it basically maintained that natural diversity. But with intrinsic rewards, that Venn score collapsed all the way down to a tiny 10.82. I mean, the curriculum essentially vanished into a single point.
It's a total artificial narrowing of the cognitive space.
It's like having a teacher who realizes the school board grading rubric only pays out if students are actively holding flashcards.
Oh, that's a great analogy.
Right. So the teacher just hands out the exact same flashcard 1,000 times in a row. Like, what is 2 plus 2? What is 2 plus 2? The technical rubric is fulfilled. The proxy metric looks great on paper, but actual education has totally collapsed.
Exactly. Grounded rewards force the teacher to stay honest because the only thing that pays out is actual student progress on the final exam.
That black box grounding signal prevents the optimization process from collapsing in on itself.
Yeah, because it's grounded, the teacher model naturally preserves the wide diversity of concepts required to tackle complex math. It generates geometry stepping stones, algebraic stepping stones, complex word problem.
It's constantly searching that high-dimensional space for the precise concepts the student is lacking.
Spot on.
Okay, so we established this grounded teacher. It successfully generates a diverse, rich curriculum of stepping stone questions. The student trains on them, breaks off that 0% plateau, and finally starts solving the impossibly hard ground truth problems.
The system works.
It works, but when the researchers actually looked closely at these synthetic questions the teacher was writing, the results completely upend our assumptions about how learning actually functions.
Yes. The correctness paradox.
The correctness paradox.
This is where the mechanics of neural learning diverge incredibly sharply from human intuition.
Because I was looking at the evaluation data from the Oracle judge. They used Claude 4.5 Sonnet to grade the teacher's curriculum, right?
They did.
I totally expected the Oracle judge to find perfectly curated answer keys. I assumed the student needed pristine data to learn. But it turned out only 32.8% of these incredibly helpful synthetic questions actually contained a fully correct mathematical solution.
Less than a third.
Less than a third. I mean, wait, really?
Yeah. The vast majority of the time, the answer key the teacher model provided to the student was objectively flawed.
Like how flawed?
I mean, it contained arithmetic failures, hallucinated steps, or just totally broken logic at the end of the chain.
Wow.
And yet, training on this curriculum of predominantly wrong answers was highly effective at getting the student unstuck on the elite benchmarks.
Okay, my brain is breaking a little bit here. How does a curriculum where 67% of the answers are technically wrong actually build intelligence?
It reveals something fundamental. For a neural network stuck in a zero-gradient plateau, the absolute truth of the final digit is not the primary bottleneck.
The final answer isn't the point.
No, the roadblock is the structure of the reasoning itself. So while the final answers were often flawed, the Oracle judge found that 64.6% of the generated questions were mathematically well posed.
Meaning they had a coherent internal logic.
Exactly. The conceptual content, the mathematical vocabulary, the sequence of operations required to even attempt the problem, all of that provides a rich gradient signal.
The structure.
Yes. The structure of the problem forces the student's neural network to activate the correct latent pathways. It forces the weights to shift in the direction of complex, multi-step thinking.
Okay, so problem structure, semantic diversity, and difficulty calibration matter far more for escaping a plateau than the final output being flawless.
Far more.
So what does this all mean? It's like having a math tutor who accidentally gives you the wrong answer key to your homework.
Okay.
But because the actual questions that tutor wrote were structurally brilliant, like forcing you to wrestle with entirely new concepts, visualize geometry in 3 dimensions, and piece together operations in a novel sequence, your brain still built the right mental muscles.
Yeah, you did the heavy lifting.
Right. So by the time you sit down for the real test, where the real answers actually matter, you ace it. The muscle was built by the struggle with the structure, not by verifying the final digit.
The coherent structure of the synthetic question provides the gradient. It tells the model how to shift its internal representations to align with target behaviors. And interestingly, when the researchers looked at the curricula generated by those failing intrinsic proxy methods we talked about,
The flashcard ones?
yeah, they actually had a much higher rate of correct answers, around 55%.
Wait, they were more accurate, but they performed worse.
Drastically worse.
Yeah.
Because they lacked the structural diversity to build varied mental muscles, they were mathematically accurate, but structurally sterile.
Wow. Just repeating verified simple pathways over and over.
Exactly. Accuracy without structural diversity provides absolutely zero momentum for generalization.
Okay, that brings up the most critical question of this entire deep dive.
Let's hear it.
If the student model is absorbing a curriculum where almost 70% of the answers are technically wrong, you'd think that bad math would eventually infect its ability to solve novel, unseen problems. Like, does this wrong answer key curriculum just hack the specific training sandbox, or does it genuinely expand the model's frontier capabilities across the board?
Right, which is the true test of any machine learning architecture. Out of distribution or owed generalization. Does the capability transfer to a totally unseen environment? Well, the researchers took the synthetic curricula optimized to help the student on 2 specific data sets, math and HARP. Then they evaluated the newly trained student on Olympiad bench.
Okay, an Olympiad bench is a notoriously difficult benchmark, right? Multi-step, competition-level mathematics that the model had never encountered during training.
Never seen it. And the stepping stones carried over beautifully. The questions optimized for math and HARP successfully improved the model's performance on Olympiad bench.
That is incredible.
It proves that the teacher wasn't generating localized hacks or memorization shortcuts for the training data. The student was fundamentally expanding its cognitive frontier.
The structurally rich, mathematically flawed synthetic questions were teaching generalizable reasoning pathways.
Exactly. And the researchers quantified just how powerful this autonomous, self-generated curriculum is by comparing it against the absolute gold standard.
Which is human curation.
Right. They evaluated what happens if you don't use the SOAR framework at all, and instead just hand the model a massive, incredibly expensive, human-curated dataset of perfectly written math problems. An Oracle dataset.
The ultimate benchmark. How does autonomous self-improvement measure up against human expert curation?
The results were staggering.
I have the numbers here. The SO method, using only the impossibly hard-failing questions as a black box grounding signal to force the base model to generate its own flawed synthetic stepping stones, was able to recover up to 75% of the performance gains you would get from training the model on that massive, curated human dataset.
75%.
75%. Just by essentially pulling latent knowledge out of its own parameters and structuring it into a gradient.
It's massive. And this architecture prompts a breathtaking thought experiment regarding the future of scientific discovery. The paper outlines this as a sort of North Star for this whole field.
Oh, I love this part. Okay, imagine a future frontier model pre-trained on the entirety of human mathematical and scientific literature. Like every physics paper, every mathematical proof ever published.
Everything.
It is highly probable that the proof for one of the great unsolved millennium problems, like the Riemann hypothesis, is already latent within that model's vast web of billions of parameters.
Yes. The knowledge required to solve it is distributed across the network. but the model cannot find the contiguous path from premise to final proof in a single attempt.
It would face a 0 out of 128 failure regime.
Exactly. You would be stuck in the dark maze.
But SOAR proves that with the right grounded asymmetric reinforcement learning loop, the AI wouldn't need a human to map the maze.
No. It could surface its own stepping stones.
It could autonomously generate the exact sequence of intermediate lemmas, simpler proofs, and structural equations needed to bridge the gap.
It could make an impossible proof learnable, purely by interacting with its own latent knowledge and verifying the downstream progress.
It shifts the entire paradigm.
It does. It shifts it from, can the model solve this, to, can the model teach itself to solve this?
It builds its own ladder to the ceiling of human knowledge just by feeling out the structure of the rungs in the dark until it finds solid ground.
Yep. And it only needs the grounding signal to verify when it finally breaks through to the top.
The decoupling of the pedagogical generation from the verifiable solving allows the system to bootstrap its own intelligence.
The implications for navigating complex high-dimensional problem spaces without human-curated datasets, they're just profound.
They really are. Wow. Okay, so we started with models utterly paralyzed on a reasoning plateau, failing elite mathematical benchmarks because the binary pass-fail grading system left them wandering without a gradient.
Stuck in the dark.
Right. And we explored how splitting a 3 billion parameter model into a teacher and a student allows the AI to decouple the act of teaching from the act of solving, tapping into latent knowledge to build a bridge it couldn't originally cross.
And we saw how grounding the teacher's rewards in actual black box student progress prevents the AI from gaming the system and collapsing the curriculum into a single repetitive loop.
Right, avoiding that flashcard trap.
Exactly. We observed how the Venn score metrics prove that semantic diversity is preserved only when the reward is tethered to actual capability expansion, not proxy metrics.
And then we unpacked the correctness paradox. The staggering reality that a highly effective curriculum doesn't even need perfect answers.
It blew my mind.
Mine too. The structural diversity, the mathematical vocabulary, and the conceptual coherence of the questions provide the necessary gradient for learning. The model doesn't need a flawless answer key. It just needs structurally brilliant questions to force its neural pathways to activate in new ways.
Proving that the struggle with the structure is the actual mechanism of learning.
Which, honestly, that realization alone redefines how we evaluate the data sets we use to train these systems moving forward.
Absolutely.
So as you process all of this, apply this framework to your own learning journey. When you are facing an insurmountable problem at work or you're trying to master a brutally difficult new skill, staring at the final goal and panicking because you keep failing, the final exam is a recipe for a plateau.
You're stuck in a sparse reward environment.
Exactly. Success isn't about leaping to the peak in one bound or waiting for a flawless manual to be handed to you. It's about finding the stepping stones. Progress is driven by asking yourself well-structured, diverse questions to build the mental muscles, even if the immediate answers you come up with are flawed.
Because the structure of the inquiry generates the momentum.
Which leaves a lingering question for you to mull over today. If an advanced artificial intelligence can break through its absolute cognitive limits and expand its frontier capabilities by wrestling with the curriculum full of technically incorrect answers, simply because the complex structure of those questions forced it to think in entirely new ways, what does that say about human education?
It's a big question.
It is. Is our intense, lifelong obsession with always having the exact right answer actually holding us back? Are we so afraid of a flawed answer key that we are failing to build the structural mental muscles we need to solve the truly impossible problems? Catch you on the next deep dive.